In this video, we will explore the inverse tangent function, right? And so much like the sine and cosine functions, when we explore the inverse tangent function, we're going to basically do the exact same process, right? If I want to find the inverse, I need to make sure that that function is one-to-one. If I look at my tangent function, which I have graphed here, we can tell that it's not one-to-one. So we're going to actually restrict it to just include one full period. And so this is the difference when I talk about inverse sine and cosine versus inverse tangent. With the inverse tangent function, we can get one entire period. Remember, I notate my axes with negative pi over 4, negative pi over 2. I have pi over 4 here and pi over 2. And our vertical asymptotes are at, sorry for the sloppiness, x equals pi over 2. And I also have one over here, x equals negative pi over 2. Okay, and so I have these points here. This point right here is a point negative pi over 2, negative 1, 0, 0, pi over 2, 1, right? Those are my points. Remember, if I look at my domain of my tangent function, right, y equals tangent of x, it is a complicated domain, but now that I've made it one-to-one, and I'm only looking at that one single part of my function, my domain is now from negative pi over 2 to pi over 2, and my range, well, I go from negative infinity to positive infinity, so it's all real numbers. Again, if I want to find my inverse function, I interchange x and y, and I solve for y. The thing that allows me to solve for y is tangent inverse of x. And what's really hiding behind here is that I know that there is an inverse here. And I know I didn't say this in the video, but what's really happening here is basically I know I can apply that inverse function to both sides of that equation up there. And I know that if I have an inverse, if I do a composition of my inverse with the regular function, then they kind of like cancel out, and that's why I'm left with y. I know I didn't say that before, but that's what's kind of standing in the background there. Because I've looked at it being one-to-one, I know that that exists, okay? Okay, my notation for my tangent function is y equals tan inverse with the negative 1 exponent of x. It's not a negative 1 exponent, but even though it looks like it. Or we can say y equals arctan of x. All right, we interchange x and y to get our tangent inverse function, and so we're going to interchange our domain and range. And so the domain is going to go from negative infinity to infinity, and the range is going to go from negative pi over 2 to pi over 2. And notice that in both of these cases, our tangent function is not defined at pi over 2 and negative pi over 2, and that's why we use these parentheses. All right, this point right here, I'm going to write it a little bit, negative pi over 4, negative 1. And so my x and y axes are going to be notated in the opposite fashion. My angles are going to be on my y-axis, and my actual trig ratios are going to be on my x-axis. So that's why I'm having negative 1, 0, and 1. And my x-axis, my y-axis, that's going to be a negative pi over 4. This one's going to be a negative pi over 2. Here I'm going to have a pi over 4, and that's going to be a pi over 2. My vertical asymptotes, when I interchange x and y, are going to now be horizontal. So I get y equals pi over 2. And here I'm going to have my other vertical asymptote now be horizontal, negative pi over 2. My ordered pair, negative pi over 4, negative 1, I go left one up pi over 4 units. Sorry, down pi over 4 units. It's negative. This point here is 0, 0, so it stays 0, 0. And this point here was pi over 4, comma 1, this point here, and so it's going to be 1 pi over 4. And I'm going to get a graph that looks something like that. It's harder to draw on here. Maybe better like that. It's a curve, it's not all the way straight. All right, but you get the picture, and you can see your domain is now all real numbers, and your range is negative pi over 2 to the power 2. In my opinion, doing the inverse tan or arctan of a value is a little bit more difficult because you can't just necessarily look at the unit circle only in order to find that value. For instance, there is no coordinate on our unit circle that we know of that has an x-coordinate of square root of 3 over 2 or a y-coordinate of square root of 3 over 2. Okay? And that's because, and the reason why we have square root of 3 over 2 is because my tangent function is y over x. And so I've got to figure out which angle has a y over x value that simplifies to square root of 3 over 2. Now, remember on our unit circle, we have our 30-degree angle or pi over 6 angle that has a coordinate of square root of 3 over 2 comma 1/2. My pi over 4 has square root of 2 over 2 square root of 2 over 2. And my pi over 3 function has a 1/2 square root of 3 over 2. When I'm thinking about arc to cotangent, I'm thinking about y over x. The only way I'm going to do a y divided by x and get a square root of 3 over 2, square root of 3 over 3 is for me to look at this right here. If I do 1/2, which is a y, divided by x, which is square root of 3 over 2, that's 1/2 times 2 over the square root of 3, which the 2's cancel. I get 1 over square root of 3. Of course, we rationalize that denominator. We're going to have the square root of 3 over 3, right? And so whatever this angle is pi over 6. I know that that's the arctan of my angle. And notice that this is an angle between negative pi over 2 and pi over 2. Make sure it's in the domain. And so I could look at the angles over here as well, but with the negatives. All right, that's our arc inverse tangent function. We're going to get to the other tangent functions, our inverse functions in class.